Welcome back. So today we are going to close out Chapter 2 by looking at how we quantify matter. And the SI unit, as we saw earlier, right, for the amount of material is the mole. So we're going to utilize this concept of the mole as a way to quantify how much matter we have. Now, how much is a mole? Well, 1 mole of something, and this is abbreviated MOL when we're doing it in calculations, equals 6.022 times 10 to the 23rd of whatever we're dealing with. So it is just a count, right? It is very similar to something like a dozen, right? In fact, we often refer to this as the chemist's dozen, right? Because it's a way that we can take a large amount of material and count it in groups as opposed to counting it individually. So, for example, if I had 144 donuts, and instead of counting them individually or talking about them individually, I wanted to say, well, how many dozen donuts do I have? Well, I automatically know that for every 1 dozen donuts, right, I have 12 individual donuts, right? Because 1 dozen is equal to 12 of whatever. And so if I do that math, my donuts cancel, and I end up with 12 dozen donuts. So it's a way that instead of saying 144 individual donuts, I'm going to just say, oh, I need 12 dozen donuts. And anybody knows that when I say I want 12 dozen, I means that I want 12 times 12, right? Or 100, what would be 144 donuts. So a mole is a similar concept, but using when we deal with really, really large numbers of things. For example, when we're counting atoms or molecules, right? Because when we're dealing even with a very small quantity, we're going to have huge amounts of atoms. So let's put this into practice. And let's say that I want to consider 1.51 times 10 to the 25 atoms. And I want to know how many moles of atoms that I have. So we're going to do something really similar here. So we're going to convert our individual number of atoms, 1.51 times 10 to the 25th atoms, and we're going to convert that into moles of atoms. And we're going to use our conversion factor, right? That 1 mole, right? And we want that on top because that's what we're trying to find. So again, dimensional analysis is equivalent to 6.022 times 10 to the 23rd, in this case, atoms. Okay? So again, my individual units cancel out, and I do my math, and this ends up working out to be 25.1 moles of atoms. So now I can talk about this huge number of atoms by just saying, oh, I got 25 moles of this particular type of atoms. So it's a way that we can count large numbers efficiently, right? Represent them by a number of moles as opposed to a number of individual atoms. You might also hear this referred to as Avogadro's number. Is another way that we talk about this number. Okay, so now that we have the basic idea of how to convert between atoms and moles, and of course, if I started out with moles and I wanted to go back to atoms, I'm going to use the same number, but I'm going to multiply by it instead of divide by it, just like if I wanted to go from 12 dozen donuts back to individual donuts, I would multiply by 12 instead of divide by 12. So we can go back and forth between how many atoms we have and how many moles of atoms we have, or moles of whatever. Now, you might be wondering at this point, why this number, right? Where does this number come from? Right? Why 6.022 times 10 to the 23rd? Seems like, kind of a random number. Well, if you remember, right, the atomic mass of carbon, right, or right, the mass of one atom of carbon is 12.01 AMUs. Now, the value of a mole is equal to the number of atoms in exactly 12 grams of carbon-12. Now remember, carbon-12 is where we got the definition of an AMU, right? Remember, an AMU is equal to 1/12 the mass of a carbon-12 atom. So one carbon-12 atom is going to have a mass of exactly 12 AMUs. And so both the definition of an AMU, right, and the quantity of a mole are both based on carbon-12, right? So this 6.022 times 10 to the 23rd is exactly the number of atoms that are in 12 grams or 1 mole of carbon-12. Now, remember, the mass on the periodic table is slightly different to this because of isotopes. Right? But since both of these quantities are centered around carbon-12, right, we can calculate the other masses, right, are based on the carbon-12, right? So this is why we use carbon-12 to get to the mole. Right? So this is where the number comes from. So we didn't just grab it out of nowhere, right? So let's think about how many moles of carbon are in 0.58 grams of carbon. So how might we go about doing this? Right? So if I have 0.58 grams of carbon, and I just said that 12 grams of carbon equals 1 mole of carbon-12 equals 6.022 times 10 to the 23rd. Well, that means that one mole of carbon atoms going to equal 12.01 grams. So we get to where the mass, the atomic mass on the periodic table in AMUs, which again is based on carbon-12, is going to be numerically the same as the mass of a mole of atoms. So if the atomic mass of carbon is 12.01, that's one atom. 1 mole of carbon atoms are going to be 12.01, but not AMU, 12.01 grams. And this would be true for all the elements, right? So 1 mole of oxygen atoms is going to be 16.00 grams. Okay? So the big point here is that what we call the molar mass is the mass of 1 mole of atoms and is numerically equal to the atomic mass but in units of grams per mole. So if you want to draw, just put it in a little bit more symbolism here. So 1 atom of carbon equals 12.01 AMU. 1 mole of carbon atoms, 12.01 grams per mole. So that mass on the periodic table actually stands for 2 things, right? It is the mass of a single atom, or the average mass of a single atom in AMUs, and it is the mass of 1 mole of atoms in units of grams per mole. So this molar mass becomes an extremely important concept when we start to quantify, right? Because we want to quantify things in terms of mass, right? So moles are great, right? Moles allow me to have a way to quantify the number of atoms in some way. But now with the molar mass, I have a way to convert my moles into grams. So if I'm dealing with carbon and I want my grams down here and I want my moles of carbon up here, I know that 1 mole of carbon is equal to 12.01 grams of carbon. And so if I go ahead and do that math, I end up with 0.58 divided by 12.01 with 0.04 and 2 significant figures, 48 moles of carbon atoms. So at this point, I have the ability to convert between atoms and between individual atoms or molecules and moles using Avogadro's number, right? Using 6.022 times 10 to the 23rd. And I now have the ability to convert between moles and grams using the molar mass of the material that I'm working with. So we're going to use these two concepts in order to convert back and forth between these three different quantities: individual items, moles of a material, and grams of a material. So at this point, let's do a couple practice problems and practice these conversions. So let's identify our two sort of main conversions, right? And that is the molar mass is equal to the amount of grams per mole, and we have 6.022 times 10 to the 23rd items is equal to 1 mole. So let's look at our first problem here. So we want to figure out how many aluminum atoms are in 6.2 grams per aluminum. So the first thing to recognize here is that we have no way to get from atoms to grams directly, right? We have a way to get from atoms to moles and a way to get from grams to moles, but we don't have a way to get directly. So we have to do this in two steps, right? We're going to have to start with grams and go to moles, and then go from moles to atoms using our molar mass, right, to go between grams and moles, and using Avogadro's number to go between moles and, in this case, aluminum atoms, right, would be our units here. So we're going to start with what we know. So I know that I have 16.2 grams of aluminum. And I need to go to moles of aluminum. So I'm going to use my molar mass. So if I look on the periodic table, right, the molar mass of aluminum equals 26.98 grams per mole. So following dimensional analysis, I know I want grams of aluminum on the bottom to cancel, and I want moles of aluminum on the top. So I follow this. I have 1 mole, weighs 26.98 grams. My grams cancel, and I would get moles if I stopped here. But I want to go ahead and do my second step. So now I want to go from moles of aluminum into aluminum atoms. And so I'm going to want moles of aluminum on the bottom to cancel out, and I'm going to want aluminum atoms on the top. So if I look at my definition of mole, I know that for every 1 mole, right, I have 6.022 times 10 to the 23rd, in this case, of aluminum atoms. And my moles of aluminum cancel out, leaving me correctly with aluminum atoms as my final unit. So if I go through and do the math, 16.2 divided by 26.98 times 6.022 times 10 to the 23rd, I get 3.62 times 10 to the 23rd aluminum atoms. Okay, so we can see here how these two conversions can be used together to allow us to convert, in this case, from grams all the way to atoms. And of course, we could start with the number of atoms and go all the way to grams. We would just do everything in reverse. And making sure we follow dimensional analysis so that our units cancel top to bottom, so we always end up with our final desired unit on the top here. Okay, let's try one more example. In this case, we want to convert 0.473 moles, in this case of lead, into how many individual grams. So, since I'm going between moles and grams, right, I'm going to utilize the molar mass, right? That's my conversion between grams and moles. So if I look on the periodic table, the molar mass of Pb equals 207.2 grams per mole. So if I set up my calculation, starting with what I know, moles of Pb. So to get my units to cancel, I of course want moles on the bottom, grams on the top. So using my molar mass, I know there are 207.2 grams per every 1 mole. My moles cancel. And if I do my math, I should end up with 3 significant figures to match this. 98.0 grams of Pb. And a quick note about significant figures. Typically, we will not use the molar masses to dictate significant figures. They aren't exact numbers, but typically our significant figures are going to be limited by the quantity that we start with, whether that's the grams of aluminum or the moles. Typically, the significant figures in our answer are going to be limited by that, not by the significant figures in your molar mass. Now, it could, right? If you knew a quantity to more than 3 or 4 significant figures, or maybe even 5, then maybe the molar mass might limit it. But typically, we're going to be guided by the initial measurement that we're given, that we're starting with, to determine the significant figures in our answer. Okay, so these are a couple practice problems. I would encourage you to do a lot more practice problems, right? The more we do of these, the better we'll get at these 2 special types of conversions, and we'll be doing these conversions a lot. Now, the nice part about them is it's all the same, right? Is we understand that we need to use molar mass to go between grams and moles, and we need to use Avogadro's number to go between moles and individual items. Then that's all we need to know. Then it won't matter if we're dealing with aluminum or water or lead, right? It's all going to be the same, right? We just have to use a different molar mass depending on what we're using, and it's always going to be 6.022 times 10 to the 23rd to go between whatever we have, individual items and moles, right? So practice, and before long, these kind of problems won't be any challenge at all for you.